to be not be in Grenoble, but in Sofia Antipolis, giving this presentation. Well, I should already correct, we were not the first to measure rotations, maybe some of the first. And I'm happy to share, a little bit of the background, the philosophy of this, why we still think it's useful, and I'll show you some recent results. I'll focus, as Martin gave me an email, I'll focus basically on the seismological aspect. So in connection with seismic source, wave propagation, tomography, rather than, which could be another topic, focus on geodetic applications. But I should note here at the very beginning that all this I thank to Karl Ulrich Schreiber, who is a specialist in ring laser technology. And the interesting story about this, he came to my office more than 20 years ago and said, well, we're building this ring laser for geodesy. It measures Earth's rotation, very highly precise. And sometimes there is another signal, for us, it's noise. And that's when an earthquake happens. Would you be interested in working with this? And I was naive and I said, yes. And so this is how I got into this field. Okay, and you already see from the pictures as application domains in terms of OBS, rupture tracking, and volcanology. These are the things I'm going to talk about. Now, I should explain the title. It's justified to call it Earth Rock and Roll because there's a lot of terminology related to these rotational components of motion. Actually, rocking and rolling is one of them. So it's just like justifying this kind of title. So what's the scope? I'll give the context a little bit first. And by the way, this is the title page of BSSA. It was in 2020. This was actually the first experiment with a blue size sensor, the rotation sensor that was created, or was basically built by this French company as a request by us. It's now a real product. And as you all know, Stromboli's summit was blown away, so this would no longer be possible to go up there at the moment. Then I want to motivate this. Why 6+ degree of freedom? And I add the plus because I should not talk about rotation. It's something gradient related. Strain and rotations are really both apples or brothers and sisters. They are related to the Wavefield gradient, and that's what makes it interesting, I think. This is the plus. So I will mostly talk about rotations, but many of the statements I make apply equally well to strain. So for seismology, it's the portable instruments that are interesting, and I'll tell you about the status of those and on field applications that we have been doing. So I want to put this first into context, and the way I see this is we are, after decades of relative silence in seismic instrumentation developments, I think it's you can call it a revolution that's happening at the moment. And I consider this along an axis of, let's say, a single point measurement to billions of sensors. And by billions of sensors, I refer to, of course, the upcoming distributed acoustic sensing technology, where this has been a statement that was made by HEU that, this allows you to have an incredible spatial resolution, billions of sensors. And of course, I would call this end of the axis basically large N, potentially low sensitivity, even that's not entirely true. DAS has a very high sensitivity, but maybe also difficulty in sort of amplitude measurement, and precise amplitude measurement on this end of the axis. Now, on the other side of the axis, it is, let's say, another motivation is making displacement and or ground motion measurements as accurately as possible. And that has to involve a measurement of rotation because of the tilt coupling of standard seismometers. So this is the other motivation on this side, making the most precise measurements possible, because if you want to get at details, you want to get, for example, non-linearities in the wave field, this is what you would want to do. And this is where, let's say, our emphasis is on the left-hand side. Now, what's at the moment is not clear is we have all these new sensing technologies, but how to combine them to solve seismological or earth science problems is not clear at all. And that's, I may say, is the key motivation for the SPIN network that has been funded and coordinated by Celine, who most of you know. And that's really exciting. So our work is basically on this side is to try and extend the three-component seismology to more components and make very precise measurements. So that's what we're talking about, is in addition to classic observations with a seismometer, ground velocity, mostly the broadband sensors, and add these three components of rotations. And usually what we measure there is rotation rate. You could also directly measure rotation, but at the moment these sensors are rotation rate sensors. Now, I show a few equations. For you, this is all, you're all seismologists, that's easy, but it's so simple, but important. Is a key motivation for many of the things we do. So let's assume you have a horizontal wave polarized in Y, so a displacement wave, plane wave propagating in X with a waveform F. So you have a functionality of kx minus omega t, and of course c equals omega by k is the phase velocity. Now take the second time derivative of this, you get acceleration, so you get an omega square, and you get the second derivative of waveform f, so f double prime. And now if we take the curl of the top equation, so the curl of the wave field, which is what we measure for a wave field, then of course this would be the half the curl of this vector here. That's now we've already one time this is the velocity, so you get rotation rate. If you take the curl of this, and you end up with a vertical component, easy to imagine. If you have a plane wave, it's the vertical component of rotation that you get with a factor of minus 1/2 k omega. And again, f prime. So first observation, the acceleration and the rotation rate have the same waveform. And now if you take the ratio of these amplitudes, you actually get minus 2 times the phase velocity. And I want to be sure that's really interesting, because that means with a point measurement for love waves at the surface, you get direct access to something that's related to the subsurface, which is the phase velocity. If you think of love waves, you immediately can imagine, okay, you get a dispersion curve and so forth. So that's very powerful, and that's something we want to exploit. So in graphical terms, you would expect that you have, let's say, a black acceleration measurement of phase, a waveform and rotation rate with equal phase, and you could, provided that the amplitudes are correct, and then that's the point. Amplitude measurements are difficult and not so accurate like phase measurements, but provided they are correct, you could play these games and extract phase velocities directly. And that's going to be very important. So I want to walk you through a couple of, let's say, cases or arguments why it's interesting to look into 6+ degree of freedom. So I read out these statements. So 6 I call plus, same for strain. Point observation provide wave field information similar to the small scale seismic arrays in terms of slowness, back azimuth, and phase separation. And I've made the point already, basically, in what I just told you in theory. And I want to say it's really quite remarkable. I should, Karin, I should have put this up. There is a paper in 1903 in German by a guy called Schlüter in Göttingen. It's amazing. It's so visionary. And it's interesting to state that at the time, the measurement of inclination was basically more accurate than measuring displacements. And he made this simple theory and said, wouldn't it be cool to measure both quantities at the same time? Then we would get access to the velocity. So there's nothing new. This is not our invention. It was there. They were there in 1903. And of course, Aki was there too. He actually applied this concept with strains in the 60s. So let me bring this point home with a data example. So this is with our ring laser near Munich. And what you see here is in black, you see a broadband measurement of transverse acceleration. This is the earthquake at Papua New Guinea in 2019, well studied. And on top of that, we superimpose it with the rotation measurement observed basically at the same site with the Romy ring laser. It's the vertical motion. And you can see, it does seem to work very well. The phase coherence or correlation is almost 1 here. And so then you can play these games and relate the amplitudes of these two traces to get at phase velocities. Before I do that, I'll show you another opportunity referring to array seismology. You can extract information on the back azimuth. So this is done here in a sliding time window over time. You can see that the color scale actually refers to basically the similarity of the waveforms as a function of assumed back azimuth. So you rotate basically the horizontal components of the standard seismometers, and you ask if the wave would come from this direction, what would be the correlation? And then you plot this, and you see that the maximum correlation fits very well, in particular in the surface wave time window, with the actual theoretical back azimuth. So that's something we will use later. And one of the questions would be whether you could actually, as a function of time, track moving sources by applying this kind of processing scheme. And at the same time, you can now relate, you can imagine you go through a time window up here and you just take, let's say, the amplitude and you divide it, and that gives you a velocity. And in particular here, you can see that it's color-coded, so the correlation coefficient is basically 1. The similarity is perfect. You see a very nice dispersion curve here for love waves. And again, that's something you could use as a measure that you can later put into an inversion scheme to come up with one-dimensional velocity models, and I'll show an example. So that's basically one aspect. In connection to this, and this is now the newest study, and it's a paper that has come out last week, you could also pose the question, if you have a sensor in a borehole, so this is a borehole here, and you measure all 3 components, and here, this is again also why I have the plus here. I at some point asked the student, Sebastian, who is now at ETH doing a PhD with Andreas Fichtner, maybe add 1 vertical strain component, because that would be easy to measure in a borehole, for example, with DAS. And the question is, with a point measurement like this, could you extract the full anisotropic elastic tensor? Very simple, theoretically, with observations from different directions. And the answer is yes. So you can, this is a theoretical study. You can come up with QP and QS waves. And I'm not going to go into details here, but you can show that this would be a probabilistic probability density function on the final estimated full elastic tensor, and you can see that the true value is the dashed black line, and you have a probability density on the tensor, and this works very well. So in theory, that's possible. And just why did we add a strain component? The reason is that, in particular, these values here, the top left, depend very much on the correct estimation of p velocities, and that you do not get very well from 6C measurements, and that's why we added basically one strain component that's actually led to a substantial improvement of the estimation for the p wave or compressibility related part of the elasticity tensor. And also, this allows with a single point measurement to come up with a bedding plane, something that might be of interest when you're in a borehole. And this is here with a similar setup. The estimation of the bedding plane. So each point is an estimation of the bedding plane from observations. With a 6 degree of freedom concept and 6 degree of freedom with a strain component, which, as you see, improves the estimation of a bedding plane, which is of course correlated to the symmetry axis of an anisotropic medium. So, case 2, ground motion gradients. So gradients, the space derivatives of the Wavefield are more sensitive to local heterogeneities. That's something that's, at least, let's say, qualitatively is pretty well known. Everyone who measures strain knows, for example, in the BFO, Black Forest Observatory, they measure strain for decades. They know it's sensitive to, for example, cavity. Now, this was always considered a nuisance. Let me demonstrate this with an experiment that's going back to a paper by Singe, and it's a collaboration with Jan Capdeville. So, simple problem, you have a source here. This is a two-dimensional model. You have you want to record something here in the middle, and if we zoom in here, we put a checkerboard-like heterogeneity, strong heterogeneity with 30–40% velocity perturbation, just to see this effect. And we put 4 sensors at the edge of these heterogeneities here. So we basically asked the questions: what do we record here? Let's say if this heterogeneity is there and if it's not there. Careful, we have a very long wavelength. The wavelength is long with respect to the heterogeneities. So when you do that, you get the following displacement recording. So you have a double couple, so you get a P wave and an S wave. Note that at the top here, there are always 4 seismograms superimposed. You don't see a difference because they're basically the same. Okay. Now, if you add the heterogeneity, the left column is basically homogeneous, and the right column is heterogeneity. So the point here is, in either a displacement measurement or an acceleration measurement, you do not see this structure here. You do not see it at all. If you zoom in, you might see a very tiny phase difference. You can kind of guess it, but the waveform is identical up to whatever 1%. Now, in terms of strains or rotations, you see a dramatic effect. You can see that, first of all, the waveforms look very different from the homogeneous case, and even the waveforms of these 4 sensors between them look very, very different. So this argument that gradient-related observations are sensitive to local structure, it can be a nuisance, but you can turn it around. It is signal. So if you think of correlation techniques, if you think of structures that maybe rapidly change over time, like a water level of a lake or something like that, or a permafrost boundary, maybe that becomes interesting. That kind of raises the motivation of looking into correlations using gradient observations. So the next case is something that's also well known. Is every seismometer is subject to tilt contamination, and that's particularly important in strong motions when you have long periods, when you measure Earth-free oscillations. and also in seismometers. And that's a simple figure from a paper by Fabian Lindner. And I'm not going to spend much time. I just want to indicate what you see here in the graph is an OBS observation. In black is the Y component, so it's a horizontal component of an ocean bottom seismometer, and the red line is the rotation or the derived rotation of the same seismometer. So the message is simple. Basically, the seismometers more or less only sees rotation. So it's a tilt-induced apparent translation. And if you know that, if you measure it, and that's shown here with a lab experiment. So at the top, this would be an angle. This is a step table, so you can impose an angle, and this is done with the blue size. Actually, this is a measurement of the blue size sensor. Another interesting aspect, this is an optical sensor with a unity transfer function. You can simply integrate and you get angle. It's cool in comparison to a seismometer. You see here the angle, and at the bottom, the blue trace is the response of the seismometer. It sees an apparent horizontal velocity, which is of course due to the tilting. And if you go into the seismometer equation, you correct for it, you can remove it, and that's done with a bottom line. You can see these tiny little signals here is an actual displacement that you do get when you tilt. You do have a remaining displacement. So that's I mentioned it at the very beginning, is in the direction of improving the quality of seismometer records. Now, the next motivation is more so far on the theoretical side, and that's something we would like to prove in the field, is you can improve the sensitivity to seismic source parameters. Now, we did quite a few theoretical experiments, always with the following kind of strategy. That's modeled here on the Totori earthquake. So you have either a point source or a finite source that is kind of embedded in a network of, let's say, n sensors here, and we compare, to be fair, we try to be fair, the sensitivity with respect to source parameters of n sensors with classic 3-component seismometers versus half the number of sensors with 6 degrees of freedom, so an additional 3 components of rotation. So in that sense, at least the number of independent measurements is the same. And I should note that when we started this, I said the expectation was when it's equally well, it's good, because then you could basically remove the number of stations by a factor of 2, which is of course much less logistics. What we use to quantify this is we basically do, we illuminate the entire model space, and which is in such a case easy, and we compare the resulting probability density function using the information gain. That's basically if you want, is the ratio, or it's related to the ratio of a prior probability density function to the posterior probability density function. If you have questions, I could talk more about it. So just as an example here, we have at the top right, you see a fault, and the fault slipped with a certain velocity, and you basically look here, this is the marginal probability density function for each of those parameters. The true value is the red line, and the black line corresponds to the PDF for the classic seismometer experiment, and the blue line corresponds to the result, or the information gain for the 6-component half the number of sensor situation. Now, the message, if we look at here, is if, let's say, if the half width of the Gaussian type function is smaller, you have a higher information gain and you have a better sensitivity. Now here, the message is, at least for the top part of the fault, it seems like the 6-component setup always leads to a better, is higher sensitive to the rupture velocity. At least it sort of diminishes at the bottom, which is something we know that the sensitivity basically decreases with depth. But that's kind of the strategy and if you do this with many, also with random combination of sensors or sensor locations, so that you exclude the effect of source receiver geometry, we can sort of statistically compare the let's say the result for using the classic 3-component, which would be the red line, with many realizations of 6-component and half the sensors. And to the right, we put the information gain. Now, and for 2 different scenarios, strike slip and normal fault. And the message here is that, at least in theory, in a synthetic world, it looks like half the sensor with 6 components, statistically significant, always are better resolved than twice the number of classic sensors. Whether this can be reproduced in the field is another question, but it's an interesting observation, and it's not entirely clear why that is the case. And the same goes for point source inversion. What is currently not clear, and that's a question you may ask, is what's the effect of the structural uncertainty? And maybe structural uncertainty will basically kill this this kind of advantage. But in any case, it seems like potentially this would allow to have reduced logistics in areas where installation of arrays is difficult. And of course, this relates to boreholes, ocean floor, volcanoes, planets, or buildings. So finally, this is again, as I said in the beginning, this kind of came out of a discussion with Pablo when he was in Munich, because we know that this back azimuth is, we can determine this quite well. Would this work on a finite fault? Can you track it? So we had this really fantastic master student who decided to go out of science. Unfortunately, he came with this really beautiful animation here, is that, if we have measurements here of both rotation and translations, we can, in a sliding time window, follow this, give it some uncertainty, and it's still, of course, this is theory, it's 2D, it's simple. You can track even a relatively complicated fault. And of course, the question was whether this works on real data. The way this works would be, again, this is a 2-dimensional problem. You have a horizontal acceleration and a rotation rate, and so this is highlighted down here. You go along this and you look for the direction of maximum correlation. That gives you a back azimuth estimate, and from this you can also derive a rupture velocity and track it back. If you assume the fault known, you can even do that with a single sensor. That's not an unrealistic case. Or, and you will see that later, if we know there is a road here and you track cars, you can estimate the velocity. So that was kind of the motivation why we think it's interesting to do this. And that's, again, highlighted with this. What I'm not talking about today is engineering applications and also planetary applications, even though there is a large EU project already going on for 2 years that's looking into applying these aspects in planetary seismology. So how about the experimental side, and how about the sensor situation? So in 2016, we basically were invited by the company iXblue to present the case to them. They built navigation sensing systems, fiber optic gyros. And to make a long story short, eventually they accepted. Yes, they start a new product line, which is the BlueSeis 3A. That's at the moment the only broadband commercially available rotation sensor. And the key question is always, is this sensor actually recording rotations? And my former postdoc, Qinchen Lin from Taiwan, he's there. Really, they have started this also a long time ago, thinking about this. They made an experiment where they put a BlueSeis sensor at the center of an array. And so at the top, again, you see an array-derived rotation in black, and the BlueSeis record in red. They are not the same because broadband. They are not the same because the BlueSeis measures higher frequencies, and an array, like in a finite difference method, is limited to a certain frequency range. But if you filter in the right frequency range, they actually, they are not normalized. This is absolute amplitude. You can see that there's an almost 1 correlation coefficient. So the answer really is, I was really excited when I saw this. Yes, we're measuring the same thing. And here's another example of, these are 2 different fiber optic gyros, different companies. It looks like we are measuring the right thing with a very high accuracy also in amplitude. So that's kind of a first verification of the accuracy of the observations. Now, how about field measurements? Now, this is now, things that we can do with the BlueSeis sensor here. One of the applications is to try and estimate the local one-dimensional velocity structure in an urban environment. Why? Because in Munich we have geothermal projects. So there is the fear, or we did have hundreds of very small earthquakes. Some of them are felt by the population. So you would like to quantify the potential ground motion for induced seismic scenarios. Now, we measure noise, so that's already a good observation. We are capable of measuring the noise level in an urban environment. And then play these games with estimating phase velocities from a point measurement. Before I do that, I would like to, for those interested in the tomography applications, I go back quite a few years now when Andreas Fichtner was still a PhD student. We posed the question, well, if you measure these phase velocities, what's the area the area of sensitivity below your receiver? And so you can apply the adjoint technique to this and visualize these so-called sensitivity kernels. And what is interesting is when you basically get these banana donut couples. Here would be a kernels. Here's a source, and that's a receiver. If you calculate kernels for rotations alone, they have this banana shape. And for velocity observations, ground velocity observations alone, you get this banana shape. But if you ask the question, but what if you have the ratio of these observations, you get what you expect. You get a kernel that's sensitive only with respect to structure close to the receiver. And that's expressed in this graph down here. And you can come up with a tomography scheme where, and that's interesting, you never extract travel times. So basically you're also, it's independent where the source is. And you can come up with, at least this is in theory, you can come up with a velocity model. So what we now going back to this single point tomography experiment, basically you measure, let's say, a spectrum. The spectrum of rotation noise is given here. And you can see that this is more or less the sensitivity level of the sensor, that below, let's say this is 1 Hertz, below 5 Hertz or so, unfortunately, the noise is so low that the sensor is not measuring it. The broadband seismometer, of course, measures the noise level correct to lower frequencies. So now what you do is you take the spectral ratio of acceleration to rotation rate, and that provides you with a dispersion relation that you can invert for a local one-dimensional velocity model. And then doing this probabilistically, you can see here this, with this, and actually I show it in the title, we also use H over V to basically complement the low frequency part. You can come up with a one-dimensional velocity model that we have some ground truth here that fits well with the lithology that's known from a borehole. So that's, I think, a very nice application of the 6th degree of freedom concept with a single station. And of course, you can understand why we think this is very exciting for planetary seismology. Because if you put one sensor on a planet, if you can do this simply by measuring noise, that's cool. Of course, the noise level on Mars is incredibly low, and there's no way at the moment this could be done with the blue side sensors, to be fair. Now, another application where I think this is useful is, of course, anywhere where you have strong motion. So this is the collapse of Kilauea volcano. Unbelievable what happened there if you compare the before and after. This is a cut through the topography. And Joachim Wassermann put the sensor here. So this is an observatory here, you can see it. And he was actually, apparently at that time, he was writing out a magnitude 5.5 quake a few kilometers away every day. And again, I make a longer story short, it's a GRL paper, these are the first dynamically measured observations of a static rotation. So you integrate, and you can see here the step in rotation. So you have a remaining tilt, and of course such observations would allow putting further constraints on this incredibly complex ring source that is happening when you have a caldera collapse, around the entire volcano rim. So that's one other possible application of this. And then coming back to this seismic source tracking, we thought that was a cool theoretical idea, submitted that paper to JGR, and it was rejected, saying basically, well, cool idea, but just, there's no data involved, and that's why we rejected it. So then we went actually back to the ring laser and looked, or more or less independently, my postdoc Shihao Yuan. So this is the situation here. Some of you know it. Here's the ring laser. That's an illustration here. So very big, 12-meter side, measures, of course, Earth's full rotation vector, but also ground rotation. And we also put a very small seismic array around it. Why? Because we observed during night coherent energy, and we thought actually it comes from this train line. Here's the S-Bahn, the commuter train, and at the night there are freight trains. So we thought it's probably coming from there. And there's also a relatively busy road here coming from this town to Munich. And so you could see, just looking at the data, this is acceleration, and this is rotation rate here. We could see this coherent energy very nicely This is from the ring laser. The first thing is, wow, it's relatively high frequency. The ring laser picks that up. And now if we do this, directional estimation along the time, and this is an example if you zoom in. So this is just using the rotation from Romy and the horizontal components from a broadband station. You can see this energy starting at, I have to think, this is 100 degrees. This would be coming from northeast and going via north to sort of southwest. And that's an incoming car from Munich, and you can estimate the velocity of this car. You get whatever 60, 70 kilometers per hour. You can also see that because there's a hill, that the velocity is usually higher on the way down and the way up. So these are all these signals here. And the reason why I suggested at the time, let's put up a small array. You can cross-validate this with an classic FK analysis, and you can see here that you basically get the same result. So that's really cool. That was with a ring laser, I should say, but we know this is not published. We know it does work with a blue size if we go close enough to the road. So it's a really very nice application. So just to mention, we have this Giotto project where we try to apply all these concepts also on structural engineering. Actually, this morning we had a nice presentation from a Polish researcher. They work also along those lines, and their results and our results indicate that these gradient measurements do provide higher resolution to detect structural damages. And of course, that's the holy grail of structural health analysis. If you would be able to locate damage and not only say, okay, there's a change in free oscillations, so something must be happening. Of course, Philippe Guéguin is working on this also in Grenoble. This is a Grenoble town hall, and we plan to have joint experiments at some point in the near future. Finally, last slide is a paper that recently came out by our previous master student. Now he's a postdoc here with a DFG project. He looked at a single station at the highest mountain in Germany, 3,000 meter high, and by a clever and complex cross-correlation analysis between different components, basically can follow that he sees a velocity change, in connection with, of course, a temperature change or a change of the permafrost in this area. And it's really very, very beautiful. A single seismometer site sees climate change. And the idea is to try and improve this with also additional gradient measurements like rotation and DAS, and that's ongoing at the moment at the Zugspitze. So to summarize, at the moment, fiber optic gyros are the most promising rotation sensing instruments for broadband seismology. That's beginning to, there might be other strategies because we are not there yet. We would like to have these sensors are not yet in our desired sensitivity range, in the sense that they do not measure below the ocean generated noise, low noise model at the moment. The ring laser is close to that, but you can't, it's not portable. Now I've showed you all these field studies, and that's just at the beginning. And these domains that I note here are, I think, promising potential applications. And there are some sites where you can get more information. In particular, we have this is the 4th special issue on rotation motion that's been published last year. These are all open access papers if you're interested. And so here I stop and I say thank you for your attention, and happy to take your questions.